Today in this video, we are going to see how the field flux density distribution takes place in a DC machine. Okay. If you see here, this is a typical DC machine shown in this figure. Here you can see here you can see here. This is the north pole of that DC machine, and this is the south pole of that DC machine. Okay. And this is the armature. This is the armature, and in the armature, I started feeding some current. Let's say here, here I say I have started feeding some current. Let us say I have started feeding some current. Let us say I, at the A1 terminal, and at the A2 terminal, I will receive the same current I back. So we already know that wherever the brushes are placed, on the either side of the brushes, we will have the opposite direction of the current. And let us say I have taken here. I have taken uh, the rotation of the generator in the clockwise direction, and as that of motor, it is in the anti-clockwise direction. So now, by applying the Fleming's right-hand rule, we can determine the currents in the under the north pole and also the currents in the south pole by just determining that by just determining the what by using the Fleming's right hand rule. Okay, okay, that is it. Now here you can see that you can see here because of this north pole of that DC machine, the field flux lines will be produced like this. If we go through like here, like this, everywhere the flux lines are produced and they complete their return path through the yoke. Okay, the flux line direction from the north pole they will emerge, and from the south to the south pole they will take it down. And if you take another flux line here like this, it's going in this way. It will take in this path like this. That is from the north pole, it is emerging and it enters into the south pole like this. These are nothing but these flux lines are nothing but what to say, it's called as nothing but field flux lines. Field flux lines. These field flux lines are produced by the MMF of the field winding. Where is the location of the field winding? The field winding is located here. I will show. Wait. Here. Here we will have the field coils like this. Okay. Like this. For south pole also there are like this. Okay. Now we will pass some DC current into these field coils. Let us say here to create a north pole here, we will dot cross here, and there will be a dot. There will be a dot. Again, here cross, here cross, and it will be dot. And by just using that right hand thumb rule, we can obtain what the direction of the flux lines. Now I say that where on the north pole I had I say on the north pole I had NF turns. On the south pole also I had enough turns, number of turns and so also enough turns. And I say the current passing through this north pole and north, the current passing through this field winding will be IF. I said, okay. Actually, how the field winding will that the field poles will be looking, I will just draw this one. This is one thing, okay. You can see like this. It is there. This is north pole and this is south pole. On this, I have given some winding, okay. Like this. And I will return this winding like this. Okay, and I will do it like this. Now what I will say, I will pass some current here. Let us say this is the IF current which is I pass here. DC current here, here, here. This is coming like this. And here it is entering. Okay. And this is here we are having that NF terms like this. And here also we are going to have the NF terms like this. So what is the MMF now? MMF per pole. We said here this north pole is there no? Here the MMF will be NF into IF. And here the MMF will be NF into IF. So that is for north pole we are going to have the MMF of NF IF, and for south pole also we are going to have the MMF of NF into IF. This is the basic. Now I have already shown these flux lines. These are going like this. So in order to have the clear picture of these flux lines, I will cut the machine at theta is equal to 0 here. Here, this is the theta. I have started measuring my theta equal to 0 from here. Okay, this is the theta is equal to 0. Here, this is theta 0, 90 degrees. And again it is going to 180 degrees. And again 270 and again 360 degrees. So I will cut this machine like this and spread this on the sheet of paper. And that diagram will look like as in the next figure we will see here. See, this is how the figure is looking. Okay. See, these are the field winding current, and in the turns the current is flowing. Now what I said here, the MMF here, it is nothing but NF into IF. Here also NF into IF. Okay. Now what I will say is that I will just show you one flux line, and we will apply the Ampere's what to say, but the Ampere's circuit law on that flux line. And I'm going to show you that flux line. I will just zoom this picture. See. And I will draw this back here like this. Okay. I'll just show you that picture, that the flux line, how it is flowing. You can see. Here, let us consider a point that is at theta is equal to 180 degrees. That point is here like this. This is the point. And also, this is just on the edge of that points is there on the q-axis, on either side of the q-axis. Now that flux line is there, no, it will take path like this, like this. It will go into this armature iron, takes return path like this. And it goes into again the field winding system like this. See how nicely it is going. Like this it will take. Okay, like this. Now we all know that from the north pole the flux lines will come out. So here the flux line direction will be like this, and here the flux line direction will be here like this. Okay, okay. And now I will mark some points here. This point, let us say this as an let us say this point as A. Again, this point is there, no? I say it is an B. And again, I say this point is there, no? Let's say this point as C. Okay, and this point as an D. Okay, D. Okay. Now what I will do? I will apply the Ampere's circuit law over this path, whatever the path I have shown you. Uh, this path, whatever the path, this path A, or this yellow line, or this yellow dotted line, I will write the Ampere's circuital law. Okay. Now I will go to for the next page and I will zoom out. Okay. This is the I will add one page. Yes. Now I will write the Ampere's circuital law for this. Hmm. How this Ampere circuital law? It is nothing but like this. It is called H BA into length for BA plus H for the path AC into length for the path AC. Okay, plus H of the path CD into L length for that CD plus H for BB into this dot. Okay, this is dot L dB, which will be equal to current enclosed that loop. Okay, the current enclosed that loop is nothing but NF into IF plus NF into IF. Okay. Now we will see what is the exact thing of this thing. I will just how it came and I will see. I'll go to the previous piece. Okay, take from the library. Where it is pictures. So, now I will discuss about this. Okay. See, just to show the Jones. See, this HBA is there, no? This HBA. This HBA is nothing but it is the value of the magnetic field intensity everywhere on this path. It is here, 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 here. Over all this path from A, B to A, from B to A, everywhere, this HBA is same. Okay. And now this LBA is there. No? LBA is nothing but length of this path, B to A. Whatever it is taking the curved path means it takes more length. Okay, that curved path length. Okay. Take a one wire, one thread and place this thread on this thing and you find that length. That is the thing LBA. Now similarly, this HAC is there. No? This is also that the magnetic field intensity everywhere on this line. here, 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 the AC up to AC. Okay, and LAC is nothing but length for this path AC length. Okay, and then HCD, HCD. For HCD, this path is there now. The CD path, the CD path here, 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 here. In the armature iron, the armature iron, this HCD. Everywhere on this line, it is same. That is HCD. Its value, magnetic field intensity value is that value. Okay, HCD. And length for that LCD is nothing. This length, like this. Thread, take that length. Okay, and similarly, we have this HDB. So HDB is nothing but this is also this length only. Okay, that on the DB, see on the DB here, here HDB, 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 HDB up to this point. Everywhere it is HDB, and that LDB is nothing but length of this DB path. This is the meaning of this thing. Okay, now while writing that writing that Ampere's loop, you can see in this loop the current enclosed, this yellow path is there. This yellow path, the current enclosed will be here. It is there one NFIF is there, and here also there is one NFIF. Same NFIF will flow here also. So the total current enclosed on this loop will be NF into IF times. IF times. That is the MMF. That is the MMF enclosed. That is what this Ampere's circuit law says. Okay. Okay. This is the thing. This is about that equation. This is that equation. Okay. We go to the next page. This is the explanation of that. This is the explanation of that this equation. Okay. This is the explanation of this equation. Now what I will say is that, now say, okay, now assumption one, this is first assumption. What we will say is that, say that flux density because of field winding, flux lines, which means that whatever the flux lines produced by that NFIF in the field poles, or yoke is BFI. Okay, BFI. And also, I will say this, explain this BFI. You go to the next, the previous page. BFI means, see here. Okay. So BFI means it is the field flux density everywhere on the field poles and yoke. That means here, 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 everywhere on this field system. This value of flux density is nothing but BFI. So if everywhere in this field system it is BFI, then on this yellow path from A to B, okay, it is also BFI. Everywhere on this yellow path also it will be from A to B. It is also a BFI on this yellow path. Okay, that is the thing. That is the meaning of the BFI. Okay, now we'll go for this. The second assumption. What is that second assumption? States that flux density because of field winding flux lines. Field winding flux lines everywhere in the armature core is nothing but armature core is nothing but BAI. Okay. Now I will show this. Tell this meaning of this BAI of the previous slide. This BAI is nothing but here. This one, this one, this one, this one. Everywhere on this armature. Here, 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 here. From everywhere in this armature. This value of flux density is nothing but BAI everywhere. So if it is BAI on everywhere on this armature iron, then we can say, on this yellow path CD, on this yellow path CD here, on this path yellow CD, this CD path, on this path also, the field, what to say, that flux density is also BAI. That is the thing you have to observe. This is the meaning of these two things. Okay, this is the meaning of these two things. Okay, this is the meaning of that BA. Okay. Like this. You keep like this. Okay, I will just close this and we'll start again. There's open. This document. Ah, this is the explanation for BFI and BA. Now we go to the add one page and okay. I will add one page here. But but we know that but we know that B is equal to mu 0 mu r into h. So I can say that h is equal to B by mu 0 mu r. Okay, that is it. Now I have the values of the BAI and BFI. Okay, and also I said that this is for the field part. No, no, no. Wait, okay, this is for armature part. Okay, and this is for what you say field part. And for the armature part, for the armature part, I said that magnetic field intensity is nothing but HCD everywhere on that line. Whatever the line is there, no? This here, this part, the CD on this line, HCD. Okay, and some for the field part, I said that the field intensity is nothing but HBA. Okay, what is that HBA? This part on this yellow part, this the field system everywhere here from this thing, HBA. Okay, that is the HBA. This is the HBA. So now what I can say is that what I can say is that okay, what I can say is that say that HBA is equal to is nothing but BFI divided by is mu 0 mu r Fi. This is the permeability of field part iron. Okay, which is nothing but relative permeability. Okay, relative permeability. And now I say now I say this mu r Fi is equal to infinity, very large, infinitely large permeability is there. Then this HBA will be equal to 0 because this is infinity, so this tends to 0. Okay, that is it. And similarly, we can write that HCD is equal to that BAI divided by mu 0 mu r AI. This is the relative permeability of armature iron. Now I say mu r AI is equal to infinity. Okay, then 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 the HCD will be equal to 0. Okay, HCD will be 0. Okay, that means That means whatever the field intensities we have got here, this HAB on this part, HAB in the field iron part will be 0. And also similarly in the armature iron part, this HCD will be 0. Will be 0. Okay. And now will be 0. I will add one page here. Now I say HAC, which will be equal to HCD, which will be equal to HG1, because this HC part and CD part both are in gap. Okay, both are in the gap, air gap. Okay, both are in air gap. I say that this HCA is equal to HCD and will be HG1, which will be equal to HG1. It is a good approximation. That means that, which means that, which means that the field intensity everywhere on this here, this path, HAC, and also HDB, HAC and HDB, it will be equal to HG1, will be equal to HG1. Okay, HG1, HG1. Here, mistake I have done. What is that? This is not HCD. This is HDB. 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 Okay. And also say that that length HAC is equal to X, and also length length LDB is also X. Okay, it will be equal to X. That means this length, whatever the length is there, this length AC and also DB, AC and also DB, both are equal to length X, which is a good approximation. You can take here, see the same length here it is there, and here also it is the same length. You can take, it's a good approximation. Okay, then now we already have that MMF equation. What is that MMF equation? This MMF equation. Copy this. Whatever this copy this thing here. This equation. Okay, I'll add to library. I'll add to next page. This equation. Okay? This equation. Now what we have got, we have already got this HBA is there, no? What we have got, this HBA, we have already got it as 0. And HAC, we have taken it as an HG1. And LAC, I took it as an that length X, and HCD is also iron part of the armature. HCD is nothing but iron part of the armature. This is also equal to 0. Okay, and now this HDB part which is there is also I took it as an HG1. The LDB I took it as an X. Okay. Now, if I then this above equation with all these assumptions will reduce as below. That is Hg1 into X plus Hg1 into X, which will be equal to 2NFIF. Okay. Now this thing can be as 2 into Hg1 into X, which will be equal to 2 into NF into IF. This two will cancel. Okay. Now what I can say that Hg1 will be equal to Hg1 will be equal to NFIF, and it is divided by X. Okay, this is the equation. Okay, what are these? This is this NFIF is nothing but MMF per pole. I have already discussed this thing. And this X is nothing but this gap length. This is gap length. Okay, this is the gap length. What is that gap length? I will show in the previous slide. This length, whatever we are getting now here, this length by thread, if you take and if you measure like this, here thread, that AC is nothing but X. Length AC is nothing but X, and also length DB by thread, so that is also X. Okay, these two lengths are nothing but X. Okay, then what is that Hg1? Hg1 is nothing but, this is nothing but on everywhere on this AC line Hg1, here, 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 and also on the DB line Hg1. We have to put them as same. An approximation we have to an equation, an assumption like that. Okay, all these things are same. Okay, we have to call these assumptions. Okay, and we have got that equation for the gap length. Okay, we'll add the page. Now I will say, now I say, now flux density at C and D as BC and BD. BC and BD. Where those are BC and BD? Here on the wedge of this armature core is there, no? Here. Okay. Here. Here and here. Here it is BC and here it is BD. Okay. I have took that assumption. I have taken that thing. BC and BD here. Okay. BC and BD. I have named the flux densities on this line here. At C and D, I named them as BC and BD. And also, I know the magnetic field intensity at C and D. What is the magnetic field intensity at C and D? The magnetic field intensity at C and D here. Here and here, which is nothing but same as done on this AC path, which is nothing but I have got previously. Then those are nothing but here also I have got as an HG1, and here also it is nothing but HG1. Okay, HG1. So BC and BD, and also HG1 and HG1. All these things I have there. Previously I have. Okay. Now what I will say, BC and BD. Okay. But BC is equal to BD. Why? Because they are very close. C and D are very close. That is at theta is equal to 180 degrees. They are on the verge of that thing. You see here. Both are very close. And this is nothing but path for theta is equal to 180 degrees. We'll just show. This is the line where theta is equal to 180 degrees on the q-axis. Okay? Theta is equal to 180 degrees here. This is nothing but a q-axis. You can say it is a q-axis. 180 degrees. Q-axis. Okay? That is it. This is on the q-axis. Okay? Q-axis. Okay? Now, we have B is nothing but mu h. B is nothing but mu h. Since that C and D are just on the surface of the armature core, I say that the permeability of air should be taken there. That is, that is, that is for air, mu r is equal to 1 and mu 0. Okay. Okay. And also I say that BC is equal to BD, and I say it as in BG1. Name it as in BG1. Is the flux density at that C and D on the surface of that armature iron. Okay, that is it. We'll add another page. Okay, that is. Now by using that formula, I can say that HG1 will be equal to BG1 divided by mu 0, because since H is equal to B by mu, because at C H is equal to Hg1 and B is equal to Bg1. So B is nothing but this is nothing but flux density. This is magnetic field intensity. Okay, because B is equal to mu H. B is equal to mu H. Okay. And now I'll get this Bg1. And I will substitute the value for Hg1. Okay, we'll substitute this value. Hg1 is nothing but NF IF by X. Okay, then you'll get Bg1 as is a mu 0 into NF into IF divided by X. Okay, that is the value of Bg1. Okay, now say X is very high means you can treat it as an infinity, very high, in the sense very high, large value, very high, large value. What is that X length? This length, this thread length, AC length, and the DB length. This is X, this is X. I said these are sufficiently large. Okay, sufficiently large. X, almost all infinity. Okay? Almost all infinity. Then Bg1 will be equal to 0. This Bg1 is nothing but at C and D. That is at q axis at theta is equal to 180 degrees. Theta is equal to 180 degrees. Okay? And that this is also, I said this is said as on the surface of the armature core. On the surface of the armature core. This is on the surface of the armature core. I will show you here on the surface of the armature core. This is a q-axis. Here it is that Bg1 is different. Here Bg1. So we have got here that Bg1 is equal to 0. Now I will indicate that Bg1 on this graph below of this thing. Whatever the thing it is there. Whatever thing is there here in the air gap. For the air gap, this value of Bg1 here is nothing but 0. Here we have got. And I plot this axis as BF. Okay. So now BF at theta is equal to 180 degrees. BF at theta is equal to 180 degrees on the surface of this armature core. On the surface of this armature core, it will be equal to 0. Will be equal to 0. And this is the explanation for this path, yellow path. This is the explanation for yellow path. Okay, this is the explanation for the yellow path. And tomorrow we will see that another path. We'll take another path and we'll see the same explanation. Okay. Thank you. Thank you. In the last class, we have seen that the derivation of that is about this. We have seen about this green line, and we have obtained that at q-axis that flux density value as 0 here. Okay, flux density value is 0. That is here on the surface of the armature iron. We have got that flux density value as 0. And today, what we are going to see is that today what we are going to uh, today what we are going to see is that uh, actually I have forgot to say one thing about that. While deriving this BF waveform, it is a field flux density waveform. We need to assume this armature current, whatever this armature current is there, no, this armature current. We have to assume that armature current IA must be equal to 0. That is armature current is 0. That is there were no this blue dots and cross. Armature current is 0. We'll derive this thing. Okay. Today will see that another flux line. Okay, like this. Today we'll start to see another flux line that is in that uh, that is flux line produced because of that field current IF only. Okay, that is I will show that flux line. That is that. I'll just zoom it out. Okay, okay. I will start in the flux line. Zoom somewhat further. Okay, yes. I will show that flux line it has in green color. Okay. I will consider a point here like this. Okay, let's say this point to be as an n. This point to be n. Okay, this point to be n. And the flux line starts here from like this. Okay, okay. Like this. Okay, here that is flux line. Let us say this point name as an M. This is M. Okay, and this flux line goes all the way here in the armature area, and it takes bend and it touches this point again. Let us say this point to be as an P. P. Okay, and this flux line like this goes all the way to that field system like this. Okay? It will take all the way like this. And it meets all the way and it travels and it meets at N. Okay, this point as N, and this point I have said it as an M, and this point I have said it is an P. Okay, and I will say the point here it is an, let us say this point as an O. This point as an O. Okay, and from the north pole the flux line is emerging, so I will represent this as emerging. Here it is going into south pole like this. Okay, like that I have taken one flux line. Now we will do the same derivation whatever previously you have done for that what is that part is then A B C D part. Similarly we will do the same derivation for M N O P part also. Okay, M N O P part. Now I will start writing that what is that Ampere's circuital law. Ampere's circuital law. Okay, go to the next page. Okay, I'll add one page here. Okay, yes. Now let me say update. Okay. Now apply Ampere circuital law. Applying the Ampere circuital law for MNOP. Okay, that is, I'll write it as an HNM into length for that NM plus HMP into length for that there is a length for that MP. Okay, and then plus H P HPO HPO into length PO plus of HON into LON, which will be equal to NF, it is IF plus, it is nothing but NF IF. Okay, now we will see the explanation of this same explanation of the ABCD path. We'll see the explanation here. Okay, just to copy this thing. Okay, add to the library and we'll go to the page. The diagram is there. Okay. Okay. First we will see HNM. What is this HNM? This HNM is nothing but that is magnetic field intensity everywhere on this NM line, everywhere on this NM line, okay? Everywhere on this NM line. And LNM is nothing but length of the this line, LNM, okay? And then we have HMP. HMP is nothing but is the magnetic field intensity everywhere on this HMP line, okay? And LMP is nothing but length for this LMP, okay? That is it. And then similarly, HPO is nothing but the value of the magnetic field intensity everywhere on this HPO line, okay? And LPO is nothing but length of that PO, okay? And then we have HON. HON is nothing but everywhere on this this path, whichever is there, no, this in field part, the ON line, everywhere the magnetic field intensity is nothing but HON, okay? And length for that O to N, this is nothing but that is LON. So now you see this green thing is there, no? This green line, full line, that is MNOP, also encloses the same NFIF plus NFIF, same MMF. It encloses the same MMF as previous one. Okay, this is the meaning of this MMF equation. Okay, this is the meaning of this MMF equation. Okay. Now, but another thing is that we have already defined that the flux density on the stator, this field system iron is nothing but BFI, which is same at everywhere in this iron. Then if it is same everywhere on this iron, then on this ON path also, then it will be the same ON path also on the same. But actually we already have known that the value of that HON, okay? We already know the magnetic field intensity at that magnetic intensity. We already know the intensity on that ON part is nothing but we defined it as an HON, okay? Now similarly for ON, this is nothing but field part iron, okay? So in the field part iron, we already defined that the flux density as is nothing but BFI, okay? Then we already know that H is equal to B by mu. So then we can say that HON is nothing but BFI divided by is mu 0 mu r Fi is the field system, okay? That is the this HON, okay? That is this HON. Now I say we already defined, or we already said that mu r Fi is nothing but infinity. So then this HON is nothing but 0, okay? This is the thing we have got observation. HON is nothing but 0, okay? HON is nothing but 0. And similarly, go to the previous slide. And similarly, we already defined that everywhere on the armature iron, the value of flux density is nothing but BAI. We already defined that flux density value as BAI. And also on this MP line, we defined that field intensity as HNP. So now we will apply the same rule here also. Now we will apply the same rule here also. So what is that rule? Here also that intensity, whatever the intensity is there, no? We'll add one page and we'll do there. Yeah. Now intensity on MP line, we have defined it as a HMP. So now HMP can be written as is BAI divided by mu 0 and mu RAI, but mu RAI is nothing but infinity. So then HMP will be getting as N0. HMP we're getting it 0. HMP we're getting it as N0. HMP we're getting it as N0. That is everywhere on this H on the line MP we're getting that the field intensity as 0, and similarly and everywhere on this line green line on NO line NO we're getting that HNO is as 0, the field intensity as 0. Okay, now I will take another assumption that let us say this NM line length of this NM to be Y, and similarly this PO line is also Y. Okay, because if you see these two lines are like symmetry, here it is also like this and here it is also like this, so I will define them as a lengths to be that what to say as an Y. Okay, that is I will start here. Okay, say that LNM is equal to LPO is equal to Y, and Y is less than X. What is this X? This X is nothing but this this X is nothing but we already defined in the previous thing. X is nothing but the length of AC and also the length of BD. Okay, since this NM is behind this AC line, you can see that length of the NM will be guaranteed less than the length of AC, and also length of OP will be guaranteed less than length of BD, because some geometry thing. It is nothing but some geometry thing. Okay, it is nothing but some geometry thing. That is, you can set that Y is guaranteed less than M by just measuring. By using scale, you can measure. Okay, that is the thing. That is the thing. And also, I will say that. Also, I will say that. And also, I will say that. Let us say that. Say that. Say that. This H and M is equal to HPO will be equal to, let us say it to be HG2, 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 and this is for gap, air gap. So what is the meaning of this thing? See here, you can see that the meaning of that H and M and HPO will be equal to HG2 means that is on everywhere on this line HM, NM, and everywhere on this line HPO, the value of magnetic field intensity is nothing but Hg2. Okay, now with this all these assumptions, we will what to say, we will say at a pace, and we say we already have the equation. No, we will, with all these assumptions, we will just modify this equation. The thing is there, no, this modify. Okay, and I said that this HNM is nothing but, what we say, this HNM is nothing but, what is nothing but, is nothing but Hg2, and this LNM is nothing but Y, and this HMP we already got it as 0, and this HPO this is also Hg2, and this length LPO is nothing but Y. and this is HON is 0. Okay. Now finally what we're going to get is that we're going to get it as this is Hg2 into y plus Hg2 plus into y should be equal to 2 NFIF. Okay. Now I said 2 Hg2y should be equal to 2 into NFIF. Okay. Now I'll cancel this 2, this 2. Okay. And then, and finally, what I have got is Hg2 will be equal to NFIF and with y. Okay. This is this thing. Okay. This is the equation I have got. And also, I said this is NFIF is nothing but MMF per pole, and this y is nothing but the gap length. Okay, that is the gap length. This is nothing but the gap length. Okay, this is Hg2, and this is how we got. And I will just show that thing in the Hg2. What is the value of Hg2? Here it is. Hg2 is nothing but everywhere on this NM line, and also everywhere on this HP, this PO line, NM line and PO line. The value of magnetic field intensity is nothing but Hg2, and with that value. Okay, Hg2 with that value. Now I will say that flux density at this point M. Here I will just zoom it further. Now I will say the flux density at this point, what is this? It's M. At M point as Bm, and the flux density at P as Bp. Okay, these are on just in the air gap only, but just on the above the surface of the armature iron. Okay, armature iron. And now we will apply that B is equal to mu H for this, because here the value of H is nothing but Hg2, and here the value of H is nothing but Hg2, and here the value of B is nothing but Bm, and here the value of B is nothing but Bp. Now we will apply B is equal to mu H here. Okay, apply the okay, I will apply this here. We will add one page. Okay, that is what I say is that is okay, that is flux density at M and P are Bm and Bp. Bm and Bp. Okay, Bm and Bp. Okay, now I said Bm as mu 0 into Hg2. Okay, and also Bp is nothing but mu 0 into Hg2. Okay, so therefore we can say that Bm is equal to Bp, because same Hg2 is there. That is y, same y length. Okay, that is y length. And now say that this Bm for B2, let us say it is an Bg2. This Bm and Bp as Bg2, and then we can say that Hg2 is equal to Bg2 divided by mu 0, or I can say it as an that Bg2 to be is mu 0 NF IF divided by let us NF IF by Y. Okay? This is an important equation. Whatever this equation we have got, this is also important equation. And now I say this is nothing but MMF per pole. mmf per port, and this is nothing but the gap length, whatever the gap length. This is nothing but the gap length. Okay, and finally we have already said that y is less than x. If y is less than x, then we can say bg1 is less than bg2. bg1 is always less than bg2, because bg1 we have got it as a 0, and since I said that y is less than as uh, y is less than as x, you can say that bg2 is always greater than bg1, because bg1 we have got it as an is mu 0 nf if divided by x. Okay, by comparing these two equations, we can say that bg1 is guaranteed less than bg2. And now I will represent this bg2 on that previous graph. See, because this whatever the thing it is there, no, this bm is nothing but we have represented as a bg2, and this bp which is there is also represented as bg2. That is, this is the value of the flux density. This is the value of the flux density. This bg2 is the value of the flux density at m, and also the value of the flux density at p. It is nothing but here. And here you can see that at m, the flux line is entering into the m. So I can say this bg2 as a positive value. And here, the flux line is going out from this m. Here, like this it is going. So I can say this bg2 here, it should be a negative. I represent this sign convention, just a sign convention. So I will represent this thing on the graph. I will represent the same thing on the graph. Uh, Here I say that here it is a positive value. So here it is a positive value. Exactly at the end, same line. Here it is positive value. And here is a P. Is nothing but negative value. So I will join this line. I'll get one graph like this. So it is a smooth curve like this. Like this. It is coming like this. This is how we are going to determine this BF waveform. That is the flux density waveform. This is for that green length. These two are for this green, and this is for that yellow line. What are the things we have got? Now, one thing, the observation we need to know about is that, see, one thing, what we have got that BG1, I say that BG1 is nothing but is mu 0 NF IF divided by X. And we have got the BG2 as mu 0 NF IF divided by Y. And these X and Y are nothing but gap lengths. That is gap lengths. That means whatever the flux is taking that path, that is nothing but those are nothing but those lengths X and Y. Okay. If you want to see, see, this AC is nothing but X. This BB is nothing but X. This NM is nothing but Y, and this PO is nothing but Y. Okay, and also we have represented BG1 and BG2. BG1 and BG2 it is at BG2 it is M, and BG2 at P, and also BG1 at C and D. So on the surface of this whatever this armature iron, on the surface of this armature iron, we are getting that value of flux density is inversely proportional to whatever the flux line is taking by that field flux lines, inversely proportional to the length of that field flux densities, inversely proportional. Okay, that is the B. What are the B we are getting? B, that is flux density OV, that is field flux density on the the surface of armature core is inversely proportional to that gap length. That gap length is inversely proportional to that gap length. Okay, is inversely proportional to the gap length. Okay, that is, what is the meaning of that thing? That is, see, if you draw such kind of flux lines, there will be many flux lines which are coming from here. There is another flux line which will come here like this, and it will here, and it is going all the way, and it will go into the south pole. Like this, another flux line, another flux line, like this, another flux line. It will take south path like this. Everything it will take like this. And also we need to observe one thing. The thing is that actually as we move from this from q axis to this north pole in this side, what are the flux lines we are going taking? These flux lines here, 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 like this. What are the flux lines we are taking? No, these lengths are decreasing when we go from q axis to north pole side. And similarly, this side also, these flux line lengths are decreasing. Okay, these flux lines lengths are decreasing. So if I say that these flux line lengths are decreasing, that means those are nothing but the gap lengths. Those gap lengths are decreasing. Whatever I have said, that x and y, they take, those gap lengths are decreasing. So if the gap lengths are decreasing, then flux density must increase because B is inversely proportional to the gap length. So from this side, I say that these gap lengths are decreasing. That means B will increase. And this side, the gap lengths are decreasing. So I say B will increase. But on this side, we on the under north pole, we have defined those values at the positive. So it will increase the positive sense here, and it will decrease in the positive sense. So I will represent those things in the graph. Here I will represent. So whatever the BF is there, no? Here it will increase. Here it will increase like this. Okay, see there now, it is increasing from here, the positive sense, and here it is increasing in the negative sense. Here it is increasing. That is, it is in the interpolar region. This interpolar region. It is interpolar region. The interpolar region, the BF wave is increasing here and in the positive sense, and it is also increasing in the positive sense. The same value here and here, it is same value, but is of negative value. Here we have not drawn this graph properly, but it is the same value. And similarly, if you see on the other side of this north pole, here also we will have the flux lines. Here also we are going to have the flux lines like this. Flux lines, flux lines, and flux lines, and flux lines. And from this side, you see that these flux line lengths, whatever the lengths you are taking, here, 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 these lengths are decreasing. Here, these are decreasing. If these are decreasing, then whatever the B we are getting, whatever the B we are getting here, they will increase because this side it is decreasing. So B will be increased because B is inversely proportional to the gap length. So I say that here this B will increase. Here it will be increased. And where they will complete these flux lines, where they will complete their return path will be going in this way. Their return path will go in this way. What way? They will, this line is there, no? Go here and it starts, it comes here and it goes here. because it is all in circular thing. And how to imagine whatever these now flux lines I'm showing you, these flux lines, this flux line will be taken like this. This is the flux lines, okay, from 270 to 90 degrees. Okay, these flux lines will come here and will be taken certain part. And here also, if you see these flux lines, this having like this, like this, like this, and like this. And from this side to this side, the length of these flux lines, those are decreasing. So that means they will be the B, whatever the B getting in this region, it will increase from this side because B is inversely proportional to the gap length. So I can say now if I plot that what are the B we have got here, if I plot them, I will be getting it as here like this from this. Here it is the distance. Okay. Here it is like this, and here is like this. That is this thing. Okay. So on end what? On end conclusion, what we say, and in the final conclusion, what we can say is that on end conclusion we can say that B on the surface of armature, this BF, surface of armature iron in the interpolar region is inversely proportional to the gap lengths. Gap lengths. This is gap lengths. Okay. Now we will see that thing in a good way. Oh no. What I will do, I will duplicate this thing and then like this now. See, I will just erase this some things. See, we have obtained this BF values here. This values is that exactly at this top here. Here it is nothing but that BF value. If I want that BF value, I will draw a line here, and it will intersect this line, and this is nothing but that BF value. And similarly here, if I want that BF value, I will draw a line here like this, and this will intersect this value here. And if I project here this one, this is that BF value. Like this, everywhere this interpolar region, the BF is defined like this. It is like this. Okay. Here it is in this interpolar region, it is, and here it is interpolar region. That is nothing but simple. It is nothing but if we are going to take this as many number of flux lines like this, then repeating this process continuously and everywhere. Here also like this. It is nothing but like this. This is how this BF wave is obtained in proper sense in the interpolar region. Why I have said interpolar region? Here the poles area is not there, and here also the pole area is not there, and here also there is no pole area. That's why I have said it as an interpolar region. In interpolar regions, The shape of the BF wave will be like this, like this. It will be like this. This is how the BF wave is obtained in the interpolar region. Okay, interpolar region. Okay, thank you, thank you. You see, actually we have got that whatever that flux density distribution in the interpolar region. Okay, we have got that interpolar region, flux density distribution in interpolar region. We have got it as we have got. What is the equation that we have got? We have got that Bg is equal to is mu 0 NF IF divided by this G. This G is nothing but it is the gap lengths in the interpolar regions. Okay, and this is variable. This is variable. That is Q axis. G is tends to infinity. Okay, tends to infinity. Okay, it is G is variable. Okay, and how this G looks. See, these are nothing but all these G's what we have got. This is one G, and this is another 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 G. And here also one G, another G, another G, another G. And here also one, two, three, four, like this many in the interpolar region. Okay, and here also this is G, 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 and G. And we have got that what is that BG? That BG. What are the BG we have got? It is nothing. That BG value is nothing but the BF value in the this BF value. Only. This BF value only we have given that name as BG. Okay, so those values are nothing but here on the surface of that armature core. Here, 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 also here, 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 here. And those values are represented by this graph, yellow graph here. And these points values are represented here. And also these are represented in this value here like this. Okay. And this is the derivation for up to what is that the interpolar region. Today we will see the derivation of this flux density distribution in the polar region. Okay. We'll see the derivation of, and one more thing I forgot to say, this flux lines on this side will take a path like this. This flux lines like this it will go. Okay, and it will start here because it is a circular thing, you know. Start here and it will complete like this. Every flux line will enclose the MMF of NF IF plus NF IF. Every flux line because everything is same. Yeah, because everything symmetrized. Okay, now we will proceed with that derivation of BF of in the polar region, that is under the poles. Under the poles. Okay. Let us say, is there any picture? Let us wait. Take. I will just run these things. Okay. Now I will take this one flux line in this what to say in the polar region. Okay, let us use scale for the flux line. Okay? I will take the flux line like this. Takes path like this. Okay, and here because of north pole the flux line will be down, and here it will be up. Okay, and now I will give you some names here like this. Here the name of the point is L, and it is some J, and it is here it is Q, and here it is L, K, K, K. And now for this line, whatever this line is there, no, that is for this line L, K, Q, J flux line. I will apply the same that Ampere's circuital law. Okay, we'll apply the Ampere's circuital law. Now, like Ampere circuital law for L, K, Q, J. Okay, path. That is H, L, K into G plus H, K, Q into L, K, Q plus H, Q, J into G plus H, J, L into L, J, L will be equal to NF IF plus NF IF. And we will see what is this thing, what is the meaning of this thing. We just show what is this. Let's back to library and we'll go to the term. Here now HLK means everywhere on this LK line, everywhere on this LK line, the value of magnetic field intensity is HLK. And as you know that here the gap length is nothing but G. So this LK length I will also take it as a G, and which is same everywhere here. What are the flux line that is taking in this under this pole? You take the length of G only. And similarly HKQ, H, K and Q, this length on this line here. What the flux line is taking in this way, no? Everywhere on this line, magnetic field intensity value is HKQ. And length for that is nothing but LKQ. And next, we're going for HQJ. Here, on this line, everywhere the magnetic field intensity is nothing but HQJ. And I have said that LQJ is nothing but G, because this length is also fixed, is the gap length, which is constant everywhere under this pole. Everywhere under this pole, this G. And here also, everywhere under this pole, what the flux line is taking? Takes the G only. And next, HJL. This is the length H, length LJL. Okay, and everywhere on this line, wherever this line is there, everywhere on this line, the value of magnetic field intensity is nothing but HJL. And also, previously we have determined that the value of flux density in the field iron is nothing but BFI. So now HLJ, HLJ, you can say that HLJ is nothing but BFI divided by this mu 0 mu r Fi. Okay, because H and B here, it is nothing. Now I say that if mu r Fi is nothing but infinity, then you can say HLJ tends to 0. HLJ or HLJ or HJL will tends to 0. And similarly, the H, whatever that field intensity on this armature iron, I have said a BI. So I can say that H K Q will be equal to BAI divided by mu 0 mu r AI. And as we already seen that this mu r AI is nothing but infinity, then you will get HKQ will be tends to 0. That is the magnetic field intensity everywhere in this is armature iron, and the magnetic field intensity everywhere in this field iron will be 0 always. And now I will say HLK is equal to HJQ is equal to HG. That is this HLK, what I have determined, and HJQ, I have taken that as an HG. H suffix G. Okay, HG and H suffix G. Okay, and now I will substitute what is that the final conclusion spot. This HLK is nothing but what I say is an HG, and this is HQ, HKQ, which you have got as 0, and HQJ. This is also HG, and HJL is nothing but 0. Okay, now you will get it as 2 HG is equal to 2 NF IF S. This is HG, and also one G will be there. H. 2 will get cancelled, and we get HG as NF IF by G. NF IF G, where NF IF is nothing but MMF per pole, and G is nothing but this is the gap length under polar region or poles, under poles. Okay, that is, I will show this HG. Everywhere here on this line it is HG, and everywhere on this line it is HG, and this length is nothing but G, and this length is nothing but G. Okay, and also I say that here the value of B, I say it as in BG, and also here I say that value of flux density as BG. Okay, now we'll apply. Now we will apply B is equal to mu H. Okay, and so that we can say that Hg is nothing but Bg divided by mu 0. Okay, and you will get that Bg value as is mu 0 NF AF divided by G. What are the previous equation? We have got the same equation. Okay, that is here it is Bg and here it is Bg with that value we have got. Whatever that value. What is that value we have got? That is Bg. Okay, that is that Bg. Now I will represent that the value of Bg uh, on this line. Here I have got that Bg, no? I will represent that value of Bg here. This is the Bg value. And here also that Bg value, what I have got, I will represent here. This is the Bg value. Why here it is positive? Because the flux line is coming from north pole. And here it is the flux line is entering to south pole. That is, here the value of flux density, the gap on the armature surface is this much. And here it is this much. Now, if I take such kind of lines, many, everywhere here, and if I do the same analysis of that Ampere circuital law, everywhere on this under poles and here also, we'll get the constant value of the flux density on the surface of this armature core because the gap length G is constant everywhere under poles. The flux line will take this path only. So this is the reason why the under the poles, the flux density in the DC machine because of the field winding, will be constant. You get the same BG. Whatever this BG we have got, you get the same everywhere under the poles. Okay, and here also we get that same BG. Okay, you get the same value. Why here it is positive? Because this because under the north pole, and here it is negative because it is under the south pole. Because it is under the south pole. Okay, because it is under the south pole. Because it is under the south pole. Because it is under the south pole and because it is under the north pole. And this is how the derivation of the BF wave for this DC machine because of the field current and the field flux lines is obtained. So on a final note, what I will say is that on a final note, what I say is that what I say is that the distribution of flux density on the surface of armature core because of field flux lines or field mmf or field current is flat chalk or approximated trapezoidal wave. This is nothing but about the BF wave. This is nothing but BF wave. And how I am getting this BF waveform? See, I'll take this trapezoidal like this smooth curve. Okay, here it is the space angle against space angle is drawn against the space angle theta, and this is nothing but BF. Okay, and here it is there under North Pole. Here it is there under South Pole. It is North Pole and it is South Pole. And this is interpolar region. Inter, and here also it is inter, and here it is also inter. Okay, that is inter. Okay, and now let us see if I consider that whatever the armature core is there, no, is there like this, and here it is there like this. Okay, and everywhere we have got that a gap on the surface. BG is nothing but is mu 0 NF IF divided by that gap length. That a gap length. Gap length. Okay. So here if you see this gap length is more, so it is 0 here. Again it is reducing here, so it is increasing. Again this gap length is reducing, it is increasing. Again it is reducing, increasing, and here it became G, same. Again here it is G, so it is same. Again it is here G, same. So again it is G, same here, and again it is G here, same. Now it was some length increased, so it reduced. Again it increased, so it reduced. So again it is increased, so it reduced, and again it increased, so it became G. In the similar way, you can check for the south pole also. And under south pole, we are taking it as negative because the flux lines direction change. And this is the thing. And also you can see that this BG, which is nothing but this is nothing but BF waveform only. This BF, whatever the BF, it is native. And everywhere that BF is considered on the surface of that armature. Here, surface of that armature. Surface of the armature. And you can see this BF is nothing but function of this field terms and also function of field current. So if I say that field current is increased, then you will get this trapezoidal waveform shifted upwards by some, because it is increased. The magnitude of that current is increased, so you will get like this. Like this, it will be increased at every space angle. In negative sense also, it will be increased. Okay. In the negative sense also, it will be increased. Okay. And if it is reduced, if the field current IF is reduced, then BF waveform also will reduce. That is, it will be reduced in this every space angle. Okay, that is it. It will be reduced. So now, if I can say, I also say that this NF IF is nothing but field MMF per pole, and I represented this thing as an FF or FF bar. It is a space vector, like that. Space vector. The meaning of this FF is nothing but NFIF, or this FF bar is nothing but NFIF. That is nothing but, you see this, take this circular thing. Whatever the circular machine is there now. Here the circular machine is there now. You start representing in this space phasor form like this. Take this one. This is nothing but Q axis like this, and this is nothing but D axis. D axis. D axis. So I started counting from theta is equal to 0 degrees here. So whatever theta it is there now, here 0, and here is nothing but theta is equal to 0, and then 90 D axis, and 180, and also 270, and here it is 360. Okay, now I represented that FF, whatever it is there now, like this. Okay, this is nothing but FF bar, and this length is nothing but FF bar length is nothing but NFIF, this length. So that is that FF peak lied at theta is equal to 90 degrees, positive peak, the meaning of this thing, and it is obtained as rectangular and distributed rectangularly over all the theta. See, this thing is there, no? See, I see. This is nothing but that FF. It is rectangular over all the space angle. Okay, its value is in the positive under north. Its value is nothing but NFIF, and in the south pole, its value is nothing but NFIF in the negative. This is negative, and this is nothing but positive. This is not positive. So this is theta is equal to 0 degrees, theta is equal to 90 degrees, 180 degrees, 270, and 360 degrees. Okay, this is how we have got that distribution of that FF. So it lies, peak value lies at 270, 90 degrees, and distributed rectangular over all the space angle. And similarly, you can also see that BF is there now. This BF, you got it as a mu 0 NFIF divided by G. Okay, this NFIF is nothing but FF. So FF and BF are in phase. So this is FF, and this is nothing but BF bar. Both are in phase. and this BF bar is trapezoidally distributed over all the space angle. Its length is nothing but this value. Its length value is nothing but this value, mu naught NFIF divided by G. Mu naught NFIF divided by G. Its length is nothing but this one. So its peak lied at theta is equal to 90 degrees because this is 0 degrees, 180 degrees, 270 degrees, and distributed trapezoidally over all the space angle. Trapezoidally, you can say like this. This is the meaning of that those space phasors BF and FF bar. Thank you. See, whatever the d-axis represented here is there, no? This d-axis is nothing but this line here is there, no? This is the d-axis. This is the line which is taken along the flux lines that are produced by the field poles. Okay, and q-axis is nothing but it is this is the perpendicular to your d-axis. This is the q-axis, and this is the d-axis. This and this same explanation. And another thing you have to observe is that whatever the field mmf ff is there, no, mmf per pole, field mmf per pole, its value is 0 at q. Its value is q. The same thing can be observed that from phasor diagram also. If you project this ff on this q axis, this is the q axis now, and this is the d axis. So if you project this ff on q axis, you will get 0 because it is an horizontal line. And similarly, bf is also 0 at q axis.